Okay, let's take a look, see what we have here. So this is exercise 5. We started this problem in class, didn't quite have time to finish it, so we're going to finish it up here. First of all, whenever we're looking at Q, this is the equation up here that we are working with. All right, it's going to take a couple of different forms, which we'll rearrange later, but in general, Q, or thermal heat, equals the mass specific heat times temperature. I'll explain the application of this a little bit differently because we're going to use water to capture energy from a chemical reaction and then use the change in temperature of that water and the characteristics of its specific heat to calculate Q. So let me diagram this out. Drawing pictures is always a good way to do this, especially when you're taking the AP exam. The AP FRQ sections, there are 7 questions, but you have 110 minutes to do so. So there's time in there to do some drawings. All right, so a coffee cup calorimeter of 100 milliliters and 1 molar NaOH and 100 milliliters of HCl are mixed. Okay, so I've got 2 beakers. I'm going to put together 100 mLs, 100 mLs. All right, and we're going to put them together, and it's going to give us a new beaker, and this one is going to give us 200 mLs. That's important because of this M in here, okay? M represents mass. Now you're like, well, wait a minute here. We're given it in milliliters. Well, the fun thing about water is that 1 gram of water also takes up 1 milliliter of space, all right? So this 200 milliliters here equals 200 grams. Now that changes a little bit by the altitude that we're at, but at standard conditions, this is reliable. All of our problems that involve this will be in standard conditions, okay? So we already have our first part here for this equation. Mass equals 200 grams. Now, what's going on inside of this reaction, okay? So we're going to use the change in temperature of the water to measure the energy, but let's take a minute and take a look at the reaction as well. So we have NaOH and we have HCl. Take a look at those two things. When we see those two things, what type of reaction comes to mind? Think about it for a second while I write this out. What will go over here? If you're thinking H plus OH will make water, and Na and chlorine will be ions in solution, you are correct, okay? So NaOH plus HCl, this is what we're going to have in this container. This is what we started off with, okay? So this one is going to produce energy, all right? And how do we know it's going to produce energy? Well, when we look at our equation here, or I'm sorry, our problem here, we start off at 24.6 degrees Celsius. And this ends up at 31.3 degrees Celsius. Okay, so we see a change. From that, we can calculate our change in temperature. Okay, so final, 31.3 degrees Celsius minus the initial of 24.6 degrees Celsius, okay, leaving us with a final temperature of 6.90 degrees Celsius. Now, the nice thing about this is we don't have to put this in Kelvin. Yay! All right, because that is the pervner, PV equals nRT. We're not using that. We can do this in Celsius. Now, if they give you in Kelvin, you can do it in Kelvin too, because 1 degree Celsius in change equals 1 degree Kelvin in change, okay? So when we're talking about change, delta T can be in K or C. It doesn't really matter because they're going to be the same, okay? So this is our mass, okay? So we've got in our equation here Q equals mass, specific heat, and temperature. We've got this one, check. We've got this one, and that's actually supposed to be delta T. Check, and now I need the specific heat. Okay, well that is listed right here. Okay, so we want to know about the Q. Okay, and this is represents the enthalpy, okay, of change. All right, so let's plug in our numbers. Q equals the mass. Now check this out. We start off with 100 and 100, but we have to do the summative mass, so this is 200 grams, okay, times specific heat, all right, and this is listed in here. This is also listed on your data sheet. It's listed right here, 4.184 joules per gram degrees Celsius. Okay, I'm going to show you how this all works. This is joules per gram degrees Celsius, and it's really helpful if we put that in our equation, because I'm going to show you how we're going to be safe. Okay, because check this out. Grams times joules times degrees Celsius, okay, that is in the numerator. This grams will be divided by the denominator grams, and this Celsius will be divided by the Celsius in the units for specific heat. Okay, so specific heat's units actually keeps us really safe, and everything is related to that. That will give us a unit in joule, and joule is our unit for energy. And in this case, we get 5.8 times 10 to the third joules. Now, some people in class ask, can we do this? And that is fine as well. You can actually put this in kilojoules, but please put a box around it. Okay? And so, in this case, all right, now how do I know if this, let's assign this a value. Is this a positive Q or a negative Q? Well, when I look at my experiment here, I went from 24 up to 31. So that means that over here, we've got energy that's being produced. So plus Q. Okay, so Q is being produced, and it's going into our water. All right, so the amount of energy that is, the enthalpy of the reaction is 5.8 e to the third joules for this reaction. All right, there we go.